let's crack on. So as an intro to the NI, I thought I'd just start back a step and look at integrity management and inspection and how they interact. So what's integrity management? It's pretty much in the name. We want to provide assurance of the integrity of assets. And in context of the NI today, for pressure equipment, we're looking at maintaining integrity of the pressure envelope of the vessel, okay? Integrity management for pressure vessels, it's a long-term activity. These things are typically designed to go into service for 30 years or so, and that operating life is typically extended. You get towards the end of the life and they want to keep the plant going even longer. So any activity around integrity management and inspection, it can cost a lot of money, and over a long time that adds up. So a cost-effective approach is really important. And that's why we've seen a greater adoption of things like RBI to align actions to risk levels. And to make effective decisions around risks, we've got to understand the risks, and part of that is understanding the condition of equipment. And one of the main ways we do that is through inspection. There's a lot of other things that give us information around the condition of a vessel, but a lot of that's theoretical. So we might do corrosion risk assessment or have an understanding of the operating conditions and the metallurgy, but the only way we can check that is through doing some inspection, measuring the actual condition to make sure that what we're estimating is realistic. And the effectiveness of your integrity management decisions depends on how relevant that information is and how good your inspection is. So what does inspection do for us? It provides us some information on the condition of equipment. So that could be, if we've got known degradation, sizing it more accurately so we can do a fitness or service assessment, or it could be going into just validate our RBI assumptions and say if there is corrosion there or not, or go in and identify and characterize different types of degradation. And we can use the information from the inspection to help us make decisions around integrity management. So how often should we be inspecting? What sort of coverage should we be doing? Does this vessel need to be re-rated, or do we need to sort of repair or replace items? And all those decisions depending on sort of appropriate inspection. And for pressure vessels, the traditional way of gathering the information around the internal condition is shut them down and then climb inside. And that's widely accepted. It's been the way it's done for many decades. And it's really good because with little to no knowledge about the operating environment, you can walk inside a vessel and have a look around. Our sensors are pretty good. They give you a broad brush, and something will stand out, and you walk up to it, have a closer look, and you get that broad brush approach. You can detect a whole range of different mechanisms. But you have to get inside. You've got to shut the thing down, which costs the industry a lot of money. And there are some mechanisms, like what Peter pointed out with the stainless, where your surface, which is visible to your eye, is very small. You can find those things with surface detection methods like dye penetrant. But some of those things, which are easy to find with internal visual inspection, are difficult to find with internal visual. Can be easier to find with NDT. And then you get non-intrusive inspection. So the main advantage, of course, is that you don't have to shut the vessel down in the first place. You can inspect it from the outside while it's still in operation. You only need to prepare the external surface, which might need some insulation removal or cleaning up the surface if it's corroded. The disadvantage there is you don't get this broad brush approach. There's no NDT technique that will just screen the whole vessel for you in one magic shot like what your eyeballs can do from the inside. So all those methods are more targeted to a specific type or morphology of degradation. So you need to know a whole lot more up front about the vessel and what degradation you expect in order to plan for a non-intrusive inspection than what you do for an internal visual. It does also give us some really beautiful quantitative data. Something with the internal visuals is you step inside, you can see a lot of things, but what you get out as a report to look at 10 years later might just be a comment like the internal surface condition is good. And that's all you get. You don't walk away with much quantitative information. If you're lucky, there might be some photos or measurements of where the corrosion is relative to a nozzle or something like that. Whereas NI, if you've applied it well, you'll have really good quantitative data. And I see a typo there. That should be NII, not IVI. So NII offers us an alternative to intrusive visual inspection that can have an equivalent or better level of assurance, but in some instances gives us significant cost savings. It's not always cheaper to do NII. It depends on the particular vessel and the costs associated with internal visual inspection. They vary a lot depending on what's in the vessel and how expensive it is to prepare that, remove chemicals in order to get a person inside. Some are easy, some are very difficult. So when I speak about NII now, and I'll look at the recommended practice in a sec, we're not speaking about any ad hoc NDT, like some point thickness measurements. That's not what we would call NII. What I mean by NII is a process where you are applying those externally applied techniques, but specifically to replace an internal visual inspection. And that means you have to do appropriate planning and evaluation of the achieved inspection to make sure that they meet specific criteria. So those differences between internal visual and non-intrusive inspection means you've got to have a different approach to the planning up front. And so it's a good almost 2 decades ago now that this Hoist joint industry project in the UK, they got a lot of big oil and gas operators and inspection companies. They came together to solve common problems like this. And internally within the JV, they had a recommended practice in as early as 2001. The first time they released that to the public was through DNV. So DNV was a member, and they agreed, just because they had publishing power, to publish and make it freely available to the rest of the world. And just at the beginning of this year, the recommended practice was updated, and Hoist has decided now to start publishing their own recommended practices because they've been coming out with the good documents. And I guess a delay in getting them reviewed through DNV, they decided to just start unleashing their own. And right from the beginning, from 2001 up until the last update, Sonomatic's been the primary author of these documents. And so we've been pretty heavily involved in writing them and applying them in industry. So some of the key updates, they've tried to make more quantified, or I guess easier to apply steps for most of the technique selection and strategies. Based on feedback, there's some rules around first in service inspection, especially in Australia, because the recommended practice was brought out of the UK, where they don't have as strict rules on first in service inspection as what we do here. But now the new section, the new RP has an appendix with some considerations around first in service inspection. They're not hard and fast rules, but gives people things to think about. Some new specific information on clad vessels and sort of design for NII. Yeah. I guess we don't have to cover all of these right now. So the overall process, it's not rocket science. It starts with an assessment to define key inspection objectives, and then we move on to building a work scope that will meet those objectives, and that'll become pretty much a working pack for the guys on site doing the jobs. You carry out the inspection on site, and then afterwards you do a detailed evaluation of the achieved inspection to ensure that you actually achieved what you set out to do. Did you meet those key requirements? And that's a really important step that a lot of people omit. We know that because we'll have a request then to implement the inspection phase of the work, and all we ever give them is a PDF of the results, no data, yet they're saying that they're doing the evaluation, which needs data. So it's a key step that's often overlooked. So I guess the starting point for an NII is to look at logical blockers, and that's not in the recommended practice explicitly, but things like, are you getting inside the vessel anyway to change out catalyst? If so, maybe NII is not your best option, because opportunistically you can do an internal visual. Or is it operating at 800 degrees Celsius where NDT is going to struggle? Once you've passed those logical sort of blockers, you can move on to the recommended practice high-level decision process, and that considers 3 main things. So it's just, how confident are you in your ability to predict the types and locations of degradation? The previous inspection effectiveness plays a role. So the more inspection information you already have, the easier it is to justify doing non-intrusive inspection, and the sort of severity and rate of degradation. So it's looking at how fast corrosion is happening and how much corrosion you've already suffered on the vessel. So it's remaining tolerance to degradation. And as a very simple example, say you've got a carbon steel vessel in hydrocarbon service. It's got some corrosion happening, but nothing drastic, and it's had some previous inspections, and it would pretty much score medium across all of those parameters, and in principle you say yes, okay, it's possible. Now we can move on to the more detailed assessment. And in that assessment phase, the key thing you want to do is look at your inspection strategy, and the recommended practice gives you 3 different strategies. There's a type A, B, and a C. So the type A, I've got to be careful I don't use any stainless or metallurgy swear words here. It covers situations where you don't expect any degradation, but because of regulation and because you want to do the right thing and manage your vessels properly, you have to do some kind of inspection, but you don't expect any degradation. So what do? You can, say a good example is a stainless vessel in hydrocarbon service, then you don't expect any degradation, but if you do, it should be reasonably spread out throughout the vessel, but it might present itself as fine pitting or even like stress corrosion cracking, which is small stuff, not always easy to find. So your strategy there is to do relatively low coverage, like 5 to 10%, but within that coverage you've got to be really sure that you can find these small flaws, so you've got to be doing really sensitive techniques. So typical vessels are corrosion resistant alloys or corrosion resistant alloy clad vessels. A type B, your easiest example is a carbon steel vessel in hydrocarbon service. You expect to see some corrosion over its life, but not to the point where you expect it to fail before its 30-year design life. So you've got a good understanding of the nature of the degradation. You expect it to be reasonably homogeneous throughout the vessel. And so you can do sampling inspection where you do reduced coverage, maybe 20 to 30% coverage of up percent, and you use that data to make estimates for the remaining condition in the rest of the vessel. And I'll come back to it again for the evaluation part for type Bs. And then a type C is where you're backed into a corner where you just can't predict anything about the degradation. So you're forced to doing a really big coverage in order to see if you can find the needle in a haystack. The easiest example is a polymer lined vessel, where the polymer lining is there to give you some protection. While it's there, you're fine, but those linings break down and we can't predict where they're going to break down. And you could even have only one area of breakdown that leads to rapid corrosion. So you're stuck in a corner and you have to do a high coverage. And recently this year, we actually, let's see if I can escape out of there. We found a needle in a haystack. So we're doing a real vessel on a real, in our campaign on a real line vessel. And we found this very small, maybe yay big pit. And that was the only one in the whole vessel. So it sort of proves why you need to do the 100% coverage thing. And I was saying you get these really nice quantified results. That's what you sort of get from a standard corrosion mapping inspection, is this good 3D depth information. And if you've got repeat inspection, yep, 5 minutes, cool. Yep, let's go. All right, so in that assessment phase, you're choosing a strategy, what's the most appropriate strategy for your vessel, and then you proceed to define some more quantitative requirements for the inspection. So before you select any techniques, you've got to define some things like coverage, location, and then how accurate do you need to be and what size flaws are you actually looking for. And if we run with our type B carbon steel vessel example, a nice conservative way to set POD is just to say, okay, well, if our corrosion allowance is 3 millimeters, let's make sure we can find defects that are half of that. I know it's very conservative, but it's a good, easy starting point. And then for a type B, because we're trying to make predictions for or estimates for the minimum thickness in uninspected parts of the vessel, measurement accuracy is really important. So you define those before you move on to selecting a technique. And I guess subconsciously you always do that if you're choosing a technique, but it's really important to document those steps to show why. So NI gives consideration to a range of techniques, and there's so many of them out there. There's always new advanced ones coming out. The sort of bread and butter ones for non-intrusive inspection are things like corrosion mapping that gives you depth or thickness information of an area, or things like phase array or time of flight diffraction for welds. And there's a range of other ones, things like charm and multi-skip for inspecting under saddle supports or other inaccessible areas. Most of those are variations on ultrasonic inspection. So you've got the 0 degree where you're looking at the thickness directly under a probe, or angled work where you're trying to skip into a weld or a nozzle connection. And just from those illustrations you can maybe appreciate, if you're not an ultrasonic person, why the geometry is important, because you've got to know where that sound is going. And then deployment wise, again, there's tons of different ways of deploying things. You get automated corrosion mapping tools, manual corrosion mapping tools. You might be looking at not just the tool itself, but how you get up to a vessel, and that could involve scaffolding or rope access. There's just loads and loads of novel gadgets or deployment tools that are out there. That one on the bottom is a domed end scanner, which we made because we had a vertical vessel. The bottom dome was sort of critical, and without inspecting that part, you couldn't justify doing NIR for the whole vessel. But the skirt didn't have a manway, so we had to make a little crawler that could go up and scan the bottom dome. So post-inspection, you need to do a detailed evaluation, and that's covering three main things. So one is conformance. So if your achieved inspection conform to the scope in terms of coverage, location, data quality, then you're saying you've met the requirements that you set up in the first place. And through the recommended practice has got rules for evaluating non-conformance and whether or not your achieved inspection was good enough, and how to deal with those. And then you've also got to look at the conditions. So what was the condition of the vessel, and I guess a combination of how good your inspection was and what condition you found the vessel to be in helps you justify the sort of formal replacement or deferment of internal visual inspection. With the Type B evaluation, I mentioned that you'd have to make estimates for the condition in uninspected areas. So sometimes when you tell people this, they think, or they look at you like they're going to start exercising you or something, because corrosion looks really random and unpredictable on a spatial sort of plane. But if you take all that data and sort it and plot it as a distribution, it really exhibits quite orderly behavior, and you can take advantage of that to make estimates for the condition in uninspected areas. How are we going for time there, Colin? Wrap it up? All right. So you can imagine the typical vessel, you might walk away with hundreds of individual scan files, so a way of managing those is really important. So what we've done in-house, it's not software we sell, but it's something we use to enable us to actually do these evaluations effectively, is some software where you, right from the beginning, you build your vessel geometry parametrically. You can collect your NDT data and assign it onto the vessel in the right positions. So that gives you something like that, which is the bigger picture, which in itself is really useful. But what's really important to us is that now it gives us ready access to the data to do the statistics and whatever else it is that we need to do. Yeah, pretty much it. All right. Thank you.
Question or two? If there's any for Tyron.
One question. Do you guys have any experience with NII on high temperature hydrogen attack?
Not really, because I think most of the applications that I've dealt with have been upstream oil and gas. Less so in refining, because I think they are shutting down more often, and yeah.
Okay,
so
thanks. It's a bit of a dark art. So
yeah. So we've done some inspections for HHA, but I've never done an NII for a vessel that's susceptible to HHA, if you put it that way. Yeah.
Good presentation, I think it's good technology. One more thing, from my experience with this, I find that sometimes the way you set your phase array or PUT up based on like standard calibration blocks. Don't always give you what you want. Knowing degradation, you know what you're looking for, right? Do you guys? Well, what's your opinion on customizing those calibration blocks? Do you have any opinion on that?
Well,
or do you still use standard blocks?
Well, you still use standard blocks, but I guess if you have a specific application and certain floor sizes that you need to ensure that you can find, then you've got to do a specific validation for that. So we're often doing validations on either a physical sample, or you get software packages like Siva that help you model ultrasonic inspection. Yeah.
Awesome. Thanks.
Great. Thanks.
Thank you. Thank you, Miles.